the solar cell. Okay, today we will discuss briefly. Completely we will discuss about that. Okay. Yeah. So already we discussed yesterday what is the difference between the solar cell and a photodiode. Okay. So in case if someone is unmuted, mute yourself. Yeah. So we discussed about the difference between the solar cell and photodiode. Okay. So in case of photodiode, what we will use, so that is connected in a conducting mode. That means we are connected in reverse bias. The diode is connected in reverse bias. Okay. In case of solar cell devices, so what we are doing means we are not connecting any external device. Okay, so that mode we will call it as photovoltaic mode. Photovoltaic mode. We will not connect any external voltage source. External voltage source here. Okay, so if we will not connect we will not connect any external source, and we will connect the load resistance. We will connect the load resistance. Okay, that is the difference between the photodiode and solar cell. Okay, now we are discuss about here. So what is the solar cell? Yeah. Solar cell is the photovoltaic device that converts light energy into electrical energy. Okay, same principle. So in that photodiode also, light energy is converted into electrical energy. Here also same. Okay, now this device work on the principle of photovoltaic effect. So based on the photovoltaic effect, it will be works. So what is the definition of photovoltaic effect? Okay, now we will discuss the definition of photovoltaic effect. The generation of voltage across the PN junction in a semiconductor due to absorption of light radiation is called photovoltaic effect. Here, so what is the photovoltaic effect? Means whenever that semiconducting material illuminated by light radiation, that means illuminated is nothing but absorbed by the light ray. So if absorb the light radiation, so what happened? That photon energy is converted into here electrical energy. Okay, in the form of voltage here. So that converts in the form of voltage. Okay, that is called as so photovoltaic effect. The devices worked based on this effect is called as photovoltaic devices. The devices worked based on this photovoltaic effect is called as photovoltaic devices. Okay, so so this is a very important definition, photovoltaic effect. Just so what is the definition mean? Just whenever the semiconducting material absorbed the light energy, that light energy is converted or light energy is stored in the form of voltages across the PN junction. Okay, that is the photovoltaic effect. Okay, now solar cell is basically a PN junction that can generate electrical power when light is illuminated. When light is illuminated. Okay, and next point, the solar cell are usually large area devices, typically illuminated with sunlight and are intended to convert the solar energy into electrical energy. Okay, so in case of photodiode, so what happened? Only that illuminated area is only intrinsic region. But in case of PN, the solar cells, in case of solar cells, that illuminated area is so total entire the PN junction, entire the PN junction. So light will be incident on the entirely total PN junction. Either P region and N region will act as a will absorbs the light. Okay, now it consists of, yeah, now we are discussing about the construction and working. Okay, first of all we are going to the construction. It consists of P-type chip. That means initially we are taking here, so P-type chip, P-type material, P-type material. Okay, on that P-type material, thin layer of N-type material is grown. Thin layer of N-type material is grown. Okay, if automatically, so in between P and N layer, so junction will be formed. Junction will be formed. So due to the diffusion process, junction will be formed in between the P and N regions. P and N regions. Okay. Now, when solar cell radiation is instant on the cell, electron hole pairs are generated in the P and N regions. Okay, so now here, so let us take the solar cell. When light is instant on the solar cell, here electron hole pairs will be generated in P region as well as N region. Okay, so that means here covalent bonds will be breaks on P region as well as, so in N region also covalent bond will breaks. So in both regions, electron hole pairs will be generated. Electron hole pairs will be generated. Now the majority of them cannot be recombined in the regions. Okay, some are recombined within the region, within the P region only. Some are recombinations will be takes place. So majority are, so does not recombine and reaches to the depulsion region. Okay, next point we will discuss on that. They reach the depulsion region at the junction where an electric field due to the space charge separator separates them. Okay, already, so PN junction will be formed. How PN junction will be formed means due to the space charge regions. Okay, so that means suppose first of all, so here P region, yeah, I will discuss here. So this is the P region and this is the N region here. Okay, so initially without light illuminated, in that P region, in that whatever the, so these holes are attracted by these electrons. Similarly, these electrons are attracted towards to the holes. So that's why what happened here, these electrons try to move this side. Okay, whenever electron is leaving at this place, what happened, space charge and space charge polarization will be occur. That means opposite charge here, opposite charge will be formed. Okay, similarly here, whenever, so hole is leaving from here to here, so here space charge polarization, okay, that is that space charge polarization is does not move from one place to another place. Okay, so at this place, so hole is hole is removed means what happened here, negatively space charge will be occur. Negative space charge will be occur. So that means here positive charge is accumulated, here negative charge is accumulated. Here positive charge is accumulated and here negative charge is accumulated. That's why, so there is no transitions, there is no further transitions. Okay, so here negative charge is accumulated. That's why this negative charge opposes these holes, all holes. So that's why, so there is no diffusion in between the P and N region. That's why what happened here, in between P region and N region, depulsion region will be formed. Depulsion region will be formed. Okay. Now, whenever light is illuminated on here, okay. So if light is illuminated here, what happened? So in that P region, so light is illuminated means covalent bond will be breaks and electron hole pair will be generated. Okay. So if electron, see here, so electrons in the P region are drawn into the N region. So whatever the electron hole pair will be generated, those will move. Electrons will move like this direction. Electrons will move so like this direction. Okay, and accumulated here. Okay. Similarly, and yeah, in N region. Okay, holes in N region drawn into P region. So these holes in N region, so try to move this side and accumulated here. That means total positive charge is accumulated here. Total negative charge is accumulated here. Okay. So due to that region, so yeah, this gives the charge accumulation on two sides of the junction. Okay. Here So this is the junction. So in this junction, this side charge will be accumulated and this side also charge will be accumulated. Okay, and produce the potential difference. So this because of this charge accumulation, because of this charge. So that means two charges are separated at a certain distance. So that means automatically, if two charges are separated at a certain distance, means it will already we discussed in last chapter. So that means okay, if charges are separated at a certain distance, means here potential will be developed. Potential will be developed due to these charge carriers. Potential will be developed this due to these charge carriers. So approximately, if you will take silicon diode, if you will take here, so general normal silicon diode, the magnitude is order of so 0.5 volts. Okay, so how much voltage will be accumulated? How much potential difference occur in between the P and N region is so 0.5 volts. 0.5 volts. Okay, that means so from each PN diode, so how much voltage will be generated? So 0.5 volts will be generated. Okay, we will get the that volt by using this load resistance. By using this load resistance, so we'll take that. So whatever potential difference will be there, so we can get the output here. We can get the output. Similarly, we can use in case of solar cell, we can use the array of so many PN junction diodes. Array of so many PN junction diodes. So these all array, so all outputs will be combined, and so we are getting the, so we'll take the so output from each PN diode, and so we'll get the large amount of voltage. We will get the large amount of voltage. Okay, from each PN diode, just we will get 0.5 volts. 0.5 volts. This is very small. Okay, if you want very high voltages, means what we will do means, so we will do the so array of the so PN junction diodes. That means so many PN junction diodes are so connected in a small area. Connected in a small area, that like that. So this array of the PN junction diode, so we can get large amount of voltages. We can get the large amount of voltages. Okay, now generally power conversion efficiency of single crystalline solar cells is the range of 10 to 30% only. Okay, that means here, so what is the power conversion efficiency? What is the power conversion efficiency means? See here, whenever light is instant on that, so only some charge carriers are accumulated here. So remaining charge carriers are recombination will be takes place. That's why so much of so we will not get, so whatever the light instant on that, so that much of efficiency we will not get. We will not get. Just efficiency is till now the range of efficiency is so maximum is 30% only. Efficiency of the solar cell. Okay, if you prepare the 100% efficient solar cells, means so we can get huge amount of power. In a small area. So till now only 30% efficiency of the solar cells are prepared. 30% efficiency of the solar cells will be prepared. Okay, if you reach more than that, means that is the achievement. Okay, now coming to the, so I think you understood the what is the concept in solar cells. Okay, any doubt on this? So what, any doubt on this concept? Once again I will explain you here. Okay, whenever light is instant on this, so first of all I will discuss about this construction. Okay, here so initially we will take the p-type region, p-type semiconducting material. Okay, p-type semiconducting material, so we'll dope n-type semiconducting material on that p-type layer. Okay, so here n-type layer is very thin. Okay, and yeah, so we'll use so one more transparent conducting film. So what is the use of the transparent conducting film? Means that protect the, so this semiconducting material. The transparent conducting film protect this semiconducting material. Okay, whatever we are taking here, so that material is protected by this transparent conducting film. Okay, due to the transparent conducting film, so light enter into the pass. So these conducting film, and light is incident on the N region as well as P region, both regions. Okay, and here we are taking the ohmic contacts for P region as well as N region. We'll take the ohmic contacts. Okay, ohmic contacts. So by using these ohmic contacts, we can take the output. We can take the, so we'll connect the here load resistance. So that resistance converts the, so here, so whatever current passing through that circuit, that convert into voltage. That convert into voltage. Okay, like that. So we can get the power here. We can get the power here. And now working, how it will be works. How it will be works. Whenever light is instant on it, whenever light is instant on it, so electron hole pairs will be generated. Already before, so there is a depulsion layer will be there in case of PN junction diode. Now, so whenever light is instant on it, suppose if P region light is light will be instant on it. Breaks, so electron hole pair will be generated. Okay, these generated electron hole pairs are so yeah, so these electrons, so try to come to the N region, try to come to the N region and accumulated on this area, accumulated at the junction, accumulated at the junction. Similarly, in N region, whenever light is instant on here, so here also electron hole pair will be generated. Here holes from N region to P region, holes try to move, holes try to move, and they will, those holes are accumulated here, those holes are accumulated here. So what happened here? So now all electrons are accumulated here and all holes are accumulated. There is a potential difference between the two regions. There is a potential difference between the two regions. So due to the, so that potential difference, due to that potential difference, so so that potential only will get the output here. We will get the output here. That potential generally we will call it as, so open circuit voltage. Open circuit voltage. Okay, so that whatever the potential developed in between the P and N regions, that potential we will call it as open circuit voltage. We will get that open circuit voltage here. Okay, now coming to the, so IV characteristics. IV character. So yeah, so if you connect the circuit, if you connect here, we are connecting the circuit. If you connect the circuit, what happen means, so due to that potential difference, so current also pass through the circuit. Current also, so here potential difference will be there. Whenever potential difference will be there, automatically current will pass through that circuit. Current pass through that circuit. In these two regions, there is a potential difference will be there. If you connect the circuit, if you connect the circuit, there will be some current passing through that circuit. Okay, now we'll discuss the, so how, what is the variation of current versus voltage. Okay, now here, so this is the diagram of IV characteristics. So IV characteristics of the solar cell. Okay, suppose here voltage will be like this. So current voltage will be some value, means so current will be like this. Okay, so up to particular value, so current will be, so like constant. So and after that it will be decreases slowly, and after particular voltage, so current will be decreases very drastically. Current will be decreases very drastically. So this is the IV characteristics of the curve. I will explain you one by one. What is the VOC? What is the ISC? Okay, so I will explain you. First of all, IV characteristics of the solar cell is shown in figure. The open circuit voltage. Open circuit voltage. This is the open circuit voltage, VOC. So the voltage across the illuminated cell at zero current is called as open circuit voltage. Open circuit voltage. Okay, I will, so I will explain you how to, experimentally how to take open circuit voltage. So that means how to make zero current also, how to make zero current, and how to take the open circuit voltage. I will explain you. So what is the VOC? Means first of all you have to know that is the open circuit voltage. Open circuit voltage. So this is VOC is the voltage across the illuminated cell at zero current. At zero current. Okay, this is about VOC. Next, ISC. ISC is the so saturated current. Saturated current. So that ISC is the current through the illuminated cell. The voltage across the cell is 0. If you will take, so voltage across the cell equal 0, so that current, that corresponding current is called as, so I saturated current, that is the ISC. Okay, so here similarly VOC means whenever we will make the current 0, whenever we will make the current 0, so that voltage we will call it as VOC. VOC. Okay, so here ISC means high saturated current. The voltage across the cell equals 0. So that current we will call it as ISC. Okay. Now the short circuit current is, so first of all we will discuss how to take VOC and ISC. Okay. For that I am explaining you here. Uh, so we are removing the, so this load resistance here. So that means for getting the output, for getting the, so voltage means we require some load resistance. We require some load resistance. Okay. So for calculating the, so I saturated current, for calculating the I saturated current, what we will do means just remove the load resistance. Just remove the load resistance and connect these two terminals with each other. Okay, here we are removing the load resistance. Here this is the load resistance. We just remove the load resistance. So and connect these two terminals. Connect these two terminals. Okay. Now, so what is the current passing through? There is no resistance means, so current passing through the diode is maximum. So there is no power loss. There is no voltage loss also. If there is no resistor means there is no voltage loss. There is no voltage loss. So that's why, so here, so current will pass to the maximum current is passing. Maximum current is passing to the circuit. Okay, that current we will call it as short circuit current. Short circuit current. Okay, so understood. So how to measure the short circuit? This experiment also there. Your solar cell experiment also there for you. Okay, so how to measure the short circuit current? Means just remove the load resistance. Just remove the load resistance and short these two terminals. And connect these two terminals. Okay, so if you connect the, so two terminals, what happens? So if there is no load resistance means maximum current is passing. There is no load resistance means there is no voltage drop also. That's why, so voltage drop across the diode is 0. Okay, now current passing through the diode is maximum. Current passing through the diode is maximum. That is called as I saturated current. See here, there is no, so at voltage will become 0, current is maximum, that is I saturated current. Okay, that is the way to calculate the, so ISC. Now coming to the how to calculate the VOC. How to calculate the VOC. So that means for that what we have to do? We have to make, so current passing through the diode is 0. Current passing through the diode is 0 means when current passing through the, so when it will be happen? If there is no connection, if there is no connection between the, and so that means there is no circuit here, there is no circuit. That means just remove the load resistance and we will leave the connections like that only. That means there is no connection between the, this N region and P region. There is no connection between the N region and P region. Now measure the voltage in between the PN junction, in between the P and N regions. So by using voltmeter, so if you measure the voltage, so there is no, if first of all we are removing the this total connection here. We are removing the total connection and we are connect the voltmeter here, one terminal, and voltmeter another terminal is we are connected here. And if you measure the voltage, so that is the maximum voltage drop across the PN junction diode. Okay, so across the PN junction diode. Okay, so that means that is called as open circuit voltage. Okay, so while measuring the open circuit voltage, what we are taking here, so current is 0. Current passing through the circuit is 0. Okay. Here we can, how to vary the current inside the circuit. How to vary the current or how to vary the voltage means by using different resistors. By using different resistors, so we can vary the voltages. We can vary the voltage as well as current. Okay, so if you use the different resistors, that means so if resistance will be high, so according to we know that formula, V is equal to IR. Okay, resistance is high means, so automatically voltage drop across the resistor is high. Okay, that's why. So if you use the high resistor, so voltage drop across the diode is high. So that means our output voltage is high. Okay, so current will become automatically low. Current will become automatically low. Okay, if you observe the graph between so I versus V. Okay, so if you change the so different resistance, so automatically voltage will be changes. Okay, so if you change the voltage, what happen? So up to particular value, current will be constant. Current will be constant. So after that, if you increase the resistance very high, okay, so voltage will be increases. Voltage will be increases, but so current is drops suddenly. Current drops suddenly. Okay, so now what is the requirement? What is the our requirement? What is our requirement means? So power. Power is our main requirement from the solar cell. Not so not only voltage, not only current. So power. What is the formula for power? So power formula is P is equal to V into I. Power formula P is equal to V into I. That means at which position so power is maximum. At which position power is maximum. So for that, so which how much resistance we have to use. How much resistor? So which type of resistor? So that means resistance range. So we have to use based on the so these IV characteristics. Okay, so at a particular value, so if you change the voltage means automatical current will be changes. So at a particular so voltage and current value, so power will become maximum. Power will become maximum. Okay, so if you change the voltage, automatically current will be changes at a particular value of the so current as well as so voltage, so power will become maximum. Okay, that is the operating point of the solar cell. That is the operating point of the solar cell. So at which current that power is maximum, that is called as Im. At which voltage that power will be maximum, that is Vm. Okay, that is denoted as a Vm. Okay, so if you use so these particular voltages, if you use this particular voltage, so voltage as well as current will get the maximum power. Maximum power. Okay, so like that, so based on this, so if you draw the diagram here, so power versus voltage diagram, so that will be, so I will draw you here. So that will be with increasing the voltage, so power will be increases like that. So it will be increased up to particular value. After that, power will be decreases. Okay, power will be decreases. So this is the so P versus so voltage drop. So this will be increases very fastly. I am writing. So this will be increases very fastly like this. Okay. So that already in your notebook it will be there that curve. So that means so at a particular value here, at a particular current and voltage, so here power will be, so this is the maximum power, this is the maximum power. So at this point we will operate the solar cell at this current value as well as voltage value will operate the solar cell. If you operate solar cell at particular these values, will get the more efficiency. Okay, now so this is about the VOC, VOC as well as ISC. So VOC means so open circuit voltage. So open circuit voltage, this is the VOC. So when we will get the open circuit voltage means so that current value will become zero. Current value will become zero. So at current will become zero. So that at that particular point, so what is the voltage drop across the diode? That is the open circuit voltage. Similarly, short circuit current. Short circuit current. Okay, whenever voltage drop across the diode is zero. Whenever the voltage drop across the diode is zero, so that current passing through the diode is maximum. That current is ISC. Okay, and so where power will be maximum? Where power will be maximum? This is the P max. This is the P max here. Okay, so this is the P maximum at a particular current and voltage values. So P will become maximum. So how to change this voltage? Already you know that. How to change that voltage here? So by using different resistors. By using different resistor at a particular resistance. At a particular resistance. So we will get the so these Im and Vm values. Okay. So that means that is the operating point of the solar cell. Operating point of the solar cell. If you operate at that point, we will get the maximum power. So this is the use of IV characteristics. So this is the, so why we will, so that means uh, before using the application, every material should be characterized. Okay, then only we can know the, so at which points it will be operated, it will give some more power. It will give the more power. So for so that's why we are finding the IV characteristics of solar cell here. So for getting the operating point. Okay. Now next point, the short circuit current is close to the photo current, while the open circuit voltage is so close to the turn on voltage of the diode. Okay, so here short circuit current is, so that means we are taking here short circuit current. That short circuit current is, so that means approximately equal to the so photo current. Okay, same, and open circuit voltage is close to the turn on voltage of the diode. Okay, so for operating the diode, we have to require some voltage. Okay, so that open circuit voltage is so turn on voltage, so turn on voltage of the diode, turn on voltage of the diode. Okay, if you operate the diode at these points, so it will be, so it will give more power. Okay, now next point, the power equals to the product of diode voltage and current. I said that P is equal to, so P is equal to, what is that, V into, 1 minute, yeah, so already we know that formula, P is equal to V into I. So P, product of voltage and P, so power P is equal to, so V into voltage into I. So current passing through the circuit. Okay, this is the, so power here, and at first increases initially with diode voltage. Already I said, so with increasing the diode voltage, what happened? Power will be increases like that. Power will be increases like that, but then rapidly goes to zero around turn on voltage. So that means after that, so it will be rapidly goes to the zero. So it will, power will be increases up to particular value. After that, so it will be rapidly goes to the zero. Okay. Around the turn on voltages of the diode. So the maximum power is attained at, so Vm and Im. Okay, the maximum power is attained at, so Vm and Im. Okay, so this is the, so I characteristics of, now coming to the conversion efficiency expression for Vm and Im. Okay, here, so there is a one equation will be there. There is a one equation will be there for calculating the, so current passing through the solar cell. Current passing through the solar cell. Okay. Yeah, the expression I is equal to I naught into e power EV by KT minus 1 minus IL. So here IL is the current passing through the load resistance. Current passing through the load resistance. I naught is the reverse saturation current. I naught is the reverse saturation current. So I is equal to I naught into e power EV by KT minus 1 minus IL. So this is the current passing through the solar cell. This is the equation for current passing through the solar cell. Okay, now we are calculating the what is ISC and VOC by using the different conditions. Okay, we obtain the expression for short circuit current. If we put, so that means how to measure the short circuit current here? While putting the voltage will be zero. If voltage will become zero, so the current, maximum current passing through the circuit is called as short circuit current. Okay, short circuit current. Okay, if you put in that above equation, so V equals 0. V equals 0. So if V is equal to 0 means e power 0. E power 0 means this is equal to 1. Okay, 1 minus 1 means this total term will become vanishes. This total term will become 0. Okay, that's why finally ISC. That means we are taking condition V equals 0. So at V equals 0, the current passing through the diode equal to, so short circuit current. Okay, short circuit current. That short circuit current ISC is equal to minus IL. Minus IL. Okay, so ISC is equal to minus IL. Okay, this is the ISC. Now, so the open circuit voltage is obtained if you put I equals 0 in the equation 1. Okay, so when we will calculate the how to calculate the open circuit voltage here? So whenever total resultant current passing through the diode equals 0. So at that situation, so that voltage we will call it as open circuit voltage. So that for calculating the open circuit voltage, what we are doing means just we are putting the I equals 0. If you put I equals 0 here, okay, so just 0 is equal to I naught into EV. So here we are putting 0. That's why this we will consider as VOC. Okay, VOC by KT minus 1 into IL. Okay, here if you simplify this equation, okay, so that means I am bringing this IL that side. Okay, so resultant will be e power EV by KT is equal to 1 plus IL by I naught. Okay, so this is the expression here. So we are taking logarithm both sides. As well as E by KT. E by KT means here that is the thermal energy. E by KT is nothing but here thermal energy. So that means yeah, KT by E. Not E by KT, KT by E. KT by E is equal to VT. That is the thermal energy here. So that equal to KT by E is equal to VT. And here we are substituting instead of V, so VOC. Because we are taking I equals 0. That's why instead of V, we are substituting VOC. Okay. Now if you we are taking logarithm on both sides. If you will take log both sides means, so this E will be exponential will be gets cancelled. So that's why EV by KT is equal to log of 1 plus IL by I naught. Okay, now simply, so this equation will become VOC by VT. So for above equation, so this equation, so this is VOC, this E by KT equal to VT. So VOC by VT. Okay, VOC by VT is equal to ln of 1 plus IL by I naught. So if you bring VT this side, VOC is equal to VT into ln of 1 plus IL by I naught. Okay, so this is here, so compared to IL by I naught. So that means I naught means reverse saturation current. That value will be very, very small. Already we discussed. In case of reverse bias, so the current will be very, very small. Okay, that's why. So IL by I naught is very, very greater than. So I naught is very small means, so IL by I naught very, very greater than 1. Na? Okay, so that's why. So we can neglect the one. Simply VOC is equal to VT into ln of IL by I naught. Okay. However, so this is the equation number 3. So this is the VOC. So now coming to the power. So we'll discuss about the power. So in next class. Okay, you have any doubts on this? You can ask. First of all, I will take the attendance.